Welcome to lesson 7.6, Dilations and Similarity in the Coordinate Plane. A quick review from previous lessons, remembering that in a similarity statement, the image is similar to the pre-image. The scale factor is always the image over the pre-image. Unless we're dealing with a modeling problem, then it's the model over the actual. The learning targets or objectives for this lesson are to be able to apply similarity properties in the coordinate plane, and secondly, to be able to use coordinate proof to prove figures are similar. A dilation, as we know, is an enlargement or reduction in the distance of all points from the center. An enlargement or reduction in the distance of all points from the center or to the center. Example 1, the dilation on a coordinate plane. We've done this before, it's just a little bit different here. It's actually not much different at all. The figure shows the position of a photo placed on the coordinate plane. Draw the border of the photo after a dilation of 3 halves. This point is currently at 3, 0. This point is currently at 3, 1, 2, 3, 4, 3, 4, and this one's at 0, 4. So we know that when we're doing a dilation in the coordinate plane, we just multiply all the ordered pairs by the scale factor. This would give us ordered pairs for A prime still at 0, 0, because when we're doing this in the coordinate plane, unless they give us a different center, we're assuming 0, 0. Otherwise, we'd have to do it by hand. 0, 3. 3 halves, that's going to be 9 halves, so D prime is going to be 9 halves, or 4.50. That'll be 9 halves, 4.5, and then 3 times 4 is 12, divided by 2 is 6, so there's C prime. And B prime is going to be 0, and then again 6. So 1, 2, 3, 4, 5, 6. 0, 6 is B prime. A prime still at 0, 0. D prime at 1, 2, 3, 4 and a half, that's 9 halves, 0, and then 9 halves, 6 for C prime. So there is what it would look like in the coordinate plane, just the border of it. Finding coordinates in similar triangles. So we need to keep in mind the scale factor here. They're telling us that TUO is similar to RSO. So this, again, is the image. This is the pre-image. So the scale factor is TU to RS. So in this particular case, TU to RS, they've done an enlargement. But we need to find the coordinates of this. Well, from TU to RS, the scale factor is going to be -9 over -12, because this point and this point match up. This is 9 units long. This is 12 units long. That's a scale factor of 3 divided by 3, 3/4. So the scale factor, given that similarity statement, is 3/4. Now, that's how they went from, that's not necessarily, shoot, hold on one second. That is completely correct. What this is saying is that this is the image, this is the pre-image. The image is smaller than the pre-image. So they're saying that triangle RSO times 3/4 gave us triangle TU0, because the image is smaller than the pre-image. So that is the correct scale factor. Now, we need to calculate these coordinates. Well, to go from here to here, they multiplied by 3/4. You can even see 3/4 times -12 is -9. I'm going to repeat the process to go from S to U, because it is S and U that match up in our similarity statement also. S, which is 0, 16, times the scale factor of 3/4 should equal the coordinates of U. 0 times 3/4 is 0. 16 over 4 is 4, times 3 is 12. So 0, 12 are the coordinates of point U. For letter B, they always tell us the similarity statement, this is image, this is pre-image. Remember, the scale factor is always image over pre-image. So if we're looking at scale factor, we're looking at MO over PO, or some combination of these over this. They also give me the coordinates of P to be negative 15, 0, of M to be negative 10, 0, and O is 0, 0. And then they give us the coordinates of Q to be 0, negative 30, and we're supposed to find the coordinates of point N. Well, and I can zoom in on that just a little bit. M to O is 10 units away. It's in a negative direction in the coordinate plane, but it's still 10 units. And O to P is 15 units away. Even if I left it as negative, it's going to reduce to, when I divide both by negative 5, 2/3. What this is saying is the scale factor to go from triangle POQ, if you multiply the pre-image by 2/3, it would equal triangle MON. Well, I have this length right here at negative 30, and it's written as an ordered pair for Q as 0, negative 30. All I have to do is multiply that by the scale factor of 2/3. That's negative 10 times 2 is negative 20. Tells me N should be at 0, negative 20. And I can see physically that that is closer to the center of dilation, as it should be. 0, negative 20. So closer to the origin. So there's the coordinates of N and the scale factor. Scale factor, coordinates. Those are the two things they were asking for. So that's how to apply the similarity ratio, the scale factor given the similarity statement, to find the points and to find the scale factor. Now we're looking at proving triangles are similar. Now in the coordinate plane, we can do this it helps us because we can actually get numbers using the distance formula. So in this particular problem, we have point E, which lucky for us is in common. And I can also use side lengths, or I could do all sides, but I think that doing 6 calculations of sides might be a little much. So I'm going to use point E, and I'm going to give a side angle side argument. I'm going to say that this is true by side angle side similarity. The angle I'm going to use is angle E. Angle E is congruent to itself by reflexive property of congruency. Now, to do the sides, I have to use the length of EG and E at EJ. So I'm going to do EG over EJ, which they did not give me those side lengths, so I'm going to have to calculate them. And then EF, because I like to do small over large, over EH. For this one, you could do the distance formula, but since it's already graphed, I'm actually going to use Pythagorean's theorem. It's 1, 2, 3, 4 units high, 1, 2, 3, 4 units long. A squared plus B squared equals C squared. So 4 squared and 4 squared, which is 16 and 16, that's 32. Taking the square root, we're also supposed to do this as exact values. X equals plus or minus the square root of 32. And since we're talking about a distance, it's going to be the positive square root of 32. 16 goes into 32 2 times. So this is 4 square roots of 2. So the distance from E to G is 4 square roots of 2. And now we're going to calculate the distance from E to J. Well, that's from here to here. So 1, 2, 3, 4, 5, 6, 7 units up. 1, 2, 3, 4, 5, 6, 7. Wait, 1, 2, 3, 4. I gotta see, is that, I might not have counted here, right? 1, 2, 3, 4, okay. 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2, 3, 4, 5, 6, 7, 8. I didn't count right vertically. I knew something was off that because the triangles that we're looking at should also be proportional, like the 4 and the 4, the 8 and the 8. So now I have for that whole length, x squared equals 8 squared plus 8 squared. 8 squared and 8 squared is 64 and 64, which is 64 times 2. Some of you figured that out already from the last problem. That's also 128, which when I go to break down to simplify the square root of 128, I'm going to have it as square root of 64 times square root of 2, which is 8 square roots of 2. So there's our ratio. Those are the exact side lengths. I'm breaking them down. Square root of 2 over square root of 2 divides away. 4 over 8 becomes 1/2. Now we just have to show that the other one also becomes 1/2. All right, so now we're going to look at EF and EH, and I'm actually going to do this on a separate sheet of paper so it doesn't get as messy. So EF and EH, we have the distance from E to F has a width of 1. So here's E and here's F, and a height of 1, 2, 3, 4. So X is our EF is our hypotenuse. 1 squared plus 4 squared equals EF squared, or call it X, or whatever variable you would like. 1 and 16 is 17. So EF is the square root of 17. 1, 2, 3, 4, yep. And we can't reduce that. It's a prime number. No factors will go into it, and no perfect including perfect squares. So the EF is the square root of 17. Next, we look at the distance from E to H. From E to H, it's left 2 and up 1, 2, 3, 4, 5, 6, 7, 8. Something's wrong. No, it's fine. No, that's actually correct. So it's left 2 and up 8. So I have 2 squared and 8 squared. Those are the legs of the triangle. The hypotenuse is EH. So EH squared equals 2 squared plus 8 squared. So that's 4 and 64, which is 68. Taking the square root of 68, the only thing that goes into it is 4. 4 times 17, I think. I'm going to double check that right now. Square root of 68. 68 divided by 4 is 17. Perfect. So square root of 4 times square root of 17 is the square root of 68. So EH is 2 square roots of 17. And so I put that down for my length, or of my distance between E and H, as 2 square roots of 17. When I go to divide, I have square root of 17 on top, square root of 17 on bottom, so that's 1. And I also get a ratio of 1/2. So we can say the triangles are similar by side angle side. We have the ratios are proportional, and the angle that touches both sets of sides that we did the ratios for are congruent. This next problem asks us to graph the image of ABC, and this again we've done before, with a scale factor of 2/3. The previous problem we had not done before. So all we need is the ordered pairs for A, 0, 3, for B, 3, 6, and for C, 6, 0. Those were given to us. That's helpful. And the scale factor is 2/3. So we just multiply every single one of those points by 2/3 to get A prime at 0, 2, B prime at times 2/3 is going to be 2, 4, and C prime at, that's 12 over 3, which is 4, 0. And so then we plot those, A prime at 0, 2, B prime at 2, 4, C prime at 4, 0. And we should see that the lines are parallel because we did not do a rotation with this. It should be in the exact same orientation. So there's A prime, B prime, and C prime, just where we would expect them. In class tomorrow, you'll be trying some of the finding the coordinates. You can even graph it if it's helpful. You'll do one like this where the coordinates are given and we have to write the scale factor and calculate the new coordinates, and one where we're going to do a proof given the points. That's it for the lesson for the video notes for 7.6. Hopefully after watching this you're able to apply similarity properties in the coordinate plane like this and like this. You understand that hopefully. And use the coordinates to do proofs of similar triangles. Have a great day.